Tonight, we're going to embark on a journey to one of the most mysterious and captivating worlds in our solar system, a place that challenges everything we think we understand about where life might exist. A world shrouded in orange haze, where rivers of liquid methane carve channels through ice mountains, where rain falls from alien skies, and where beneath a frozen crust, a hidden ocean of liquid water might harbor forms of life, utterly unlike anything we have ever imagined. We're going to explore Titan, Saturn's largest moon, and we're going to discover why scientists believe this distant, frigid world might be one of the most promising places in our entire solar system to search for life beyond Earth. Before we begin, if you enjoy these deep explorations of the cosmos and the profound questions they raise about our place in the universe, a quick like or subscribe would really help the channel grow. Now let's begin our voyage to the realm of Saturn, where Titan awaits. To truly appreciate what makes Titan so remarkable, we first need to understand its place in the cosmic neighborhood. Saturn, the sixth planet from the Sun, orbits at an average distance of about 1.4 billion kilometers from our star. That's roughly 9.5 times farther from the Sun than Earth. At this tremendous distance, sunlight is approximately 100 times weaker than what we experience here on our planet. Saturn is a gas giant composed primarily of hydrogen and helium, famous for its spectacular ring system that has captivated human observers since the invention of the telescope. But surrounding this magnificent ringed world is an even more remarkable collection of moons. Saturn possesses more than 140 confirmed natural satellites, ranging from tiny irregular chunks of ice and rock to substantial worlds in their own right. Among all these moons, Titan stands alone. It is Saturn's largest satellite by a considerable margin, measuring approximately 5,150 kilometers in diameter. To put this in perspective, Titan is larger than the planet Mercury, which has a diameter of only about 4,880 kilometers. Titan is the second largest moon in the entire solar system, surpassed only by Jupiter's Ganymede, which is slightly bigger at 5,268 kilometers across. If Titan orbited the Sun directly rather than Saturn, it would easily qualify as a planet in its own right. Its substantial size means it possesses enough gravity to hold onto an atmosphere, and this is where Titan becomes truly extraordinary. The mass of Titan is approximately 1.35 times 10 to the 23rd kilograms, roughly 1.8% of Earth's mass. While this might seem modest compared to our planet, it gives Titan a surface gravity of about 1.35 meters per second squared, approximately 1/7 of Earth's gravity. On Titan, you would weigh only about 14% of what you weigh on Earth. An astronaut weighing 90 kilograms on Earth would weigh only about 12.5 kilograms on Titan's surface. This low gravity has important implications for everything from atmospheric escape to the potential for flight within the atmosphere. Titan's bulk density of approximately 1.88 grams per cubic centimeter tells us something important about its composition. For comparison, Earth has a density of about 5.51 grams per cubic centimeter, reflecting our planet's large iron core. Titan's much lower density indicates that it is composed primarily of less dense materials, specifically a mixture of water ice and silicate rock in roughly equal proportions. Scientists estimate that Titan is approximately 50% rock and 50% ice by mass. This composition is typical of the large moons of the outer solar system, which formed in regions cold enough that water ice was abundant in the primordial solar nebula. Titan orbits Saturn at an average distance of approximately 1.22 million kilometers, completing one orbit in about 15.95 Earth days. This orbital period is also Titan's rotation period because, like Earth's moon, Titan is tidally locked to its parent planet. This means one side of Titan always faces Saturn, while the opposite hemisphere always faces away. A person standing on Titan's Saturn-facing hemisphere would see the ringed planet dominating the sky, its apparent diameter spanning more than 5 degrees of arc, roughly 10 times larger than the full moon appears from Earth. However, this spectacular view would be hidden by Titan's thick atmospheric haze most of the time. The tidal locking of Titan to Saturn has important consequences for the moon's internal structure and evolution. Tidal forces from Saturn constantly flex and squeeze Titan's interior, generating heat through friction. This tidal heating contributes to the thermal energy budget of the interior, potentially helping to maintain liquid water in the subsurface ocean. The heating is not as intense as that experienced by Jupiter's moon Io, which is the most volcanically active body in the solar system, but it is significant enough to influence Titan's geology and interior structure. Saturn's gravitational influence also causes Titan's orbit to be slightly elliptical rather than perfectly circular. The eccentricity of approximately 0.029 means that Titan's distance from Saturn varies by several tens of thousands of kilometers over the course of each orbit. This varying distance changes the strength of the tidal forces, causing Titan to flex slightly more when it is closer to Saturn and relax when it is farther away. These periodic flexings may pump energy into the interior and could drive geological processes like cryovolcanism. But what truly sets Titan apart from every other moon in our solar system is something far more significant than mere size. Titan possesses a dense, substantial atmosphere. It is the only moon anywhere in our solar system known to have a fully developed atmosphere consisting of more than just trace gases. And this atmosphere is not some thin wisp of molecules, barely clinging to the surface. Titan's atmospheric pressure at ground level is approximately 1.5 times that of Earth's atmosphere at sea level. If you could somehow stand on Titan's surface without succumbing to the extreme cold, you would feel noticeably more air pressure pushing against you than you do right now, wherever you happen to be listening to this. This atmospheric presence fundamentally transforms Titan from just another icy moon into something profoundly different. It makes Titan a world with weather. It makes Titan a world with a cycle of evaporation, cloud formation, precipitation, and surface flow, remarkably analogous to Earth's water cycle, though operating with entirely different liquids at entirely different temperatures. It makes Titan a world where complex organic chemistry is constantly occurring, driven by the interaction of sunlight with atmospheric gases, producing an ever-accumulating inventory of carbon-rich compounds that rain down upon the surface like cosmic soot. And perhaps most tantalizingly, it makes Titan a world that may have harbored the conditions necessary for life to arise, whether in forms we would recognize or in forms so alien They would challenge our very definitions of what life means. The presence of Titan's atmosphere was not always known to us. For centuries after its discovery, Titan was simply another point of light in telescopes, a small companion faithfully circling the ringed planet. Understanding what Titan truly was and why it might matter so profoundly in our search for life beyond Earth required centuries of patient observation, decades of theoretical speculation, and ultimately the dispatch of spacecraft across more than 1 billion kilometers of interplanetary space to pierce the veil of orange haze and reveal the secrets beneath. That story of discovery is where our exploration must begin. The history of human awareness of Titan stretches back nearly 4 centuries to an era when the telescope was still a revolutionary new instrument transforming our understanding of the heavens. In the year 1655, the Dutch astronomer Christian Huygens turned a telescope of his own design toward the planet Saturn. Huygens was not merely an astronomer, but a polymath of extraordinary talent, a physicist, mathematician, and inventor who would go on to make fundamental contributions to our understanding of light, time, and motion. Along with his brother Constantine, Christian had developed improved techniques for grinding and polishing telescope lenses, reducing the optical aberrations that plagued earlier instruments and enabling clearer, sharper views of celestial objects. When Huygens observed Saturn through his new 50-power refracting telescope on March 25, 1655, he was primarily interested in the planet's strange appearance, which earlier observers, including Galileo, had noted, but failed to correctly interpret. But as he studied Saturn, Huygens noticed something else: a small point of light near the planet that moved in a way consistent with being a satellite in orbit. Over subsequent observations, he confirmed that this was indeed a moon, and he announced his discovery in a tract titled De Saturni Luna Observatio Nova, which translates as a new observation of Saturn's moon. Huygens called his discovery Luna Saturni, Latin for moon of Saturn. It was the first moon of Saturn ever discovered by humans, and only the 6th planetary satellite known at the time, following Earth's moon and the 4 large moons of Jupiter that Galileo had discovered in 1610. The name Titan would not be applied to this moon until nearly 2 centuries later, when the English astronomer John Herschel, son of the famous William Herschel, proposed naming Saturn's moons after the Titans of Greek mythology. These were powerful deities who preceded the Olympian gods, children of Uranus and Gaia, primordial beings of immense power. The name proved appropriate in ways Herschel could never have anticipated, for Titan would eventually reveal itself to be a world of truly primordial character, preserving chemical conditions that may echo the earliest epochs of our own planet's history. For more than 2.5 centuries after Huygens' discovery, Titan remained essentially a mystery. Telescopes improved gradually over the generations, but even the best instruments could resolve little more than a small orange disk when pointed at this distant world. Astronomers could track Titan's orbit around Saturn, calculating that it completed one circuit approximately every 16 Earth days, at a mean distance of roughly 1.2 million kilometers from the planet's center. They could estimate Titan's brightness and make rough calculations about its size. But the physical nature of the moon, what it was made of, whether it had any significant surface features, whether it possessed an atmosphere, all of this remained unknown. the first hint that Titan might be something more than just another ball of ice and rock came in 1903 when the Spanish astronomer José Comas Solá, working at the observatory in Barcelona, made careful observations of Titan and noticed something curious. The disk of the moon appeared darker around its edges than at its center, a phenomenon known as limb darkening. This effect can occur when light must pass through more atmosphere at a shallow angle near the edge of a disk than when passing straight through at the center. Comas Solá's observation suggested that Titan might possess an atmosphere substantial enough to cause this visible darkening effect, but the evidence was not conclusive, and the finding remained a tentative hypothesis rather than an established fact. The definitive discovery of Titan's atmosphere came in 1944, during the dark years of World War II, when the Dutch-American astronomer Gerard Peter Kuiper turned the power of modern spectroscopy toward Saturn's largest moon. Kuiper was working at the McDonald Observatory in Texas, using techniques that allowed him to analyze the specific wavelengths of light reflected from celestial objects. When he examined the spectrum of light from Titan, he found unmistakable absorption bands, characteristic of methane gas. Methane, a simple molecule composed of one carbon atom bonded to 4 hydrogen atoms, was absorbing certain wavelengths of light passing through Titan's atmosphere, leaving telltale dark lines in the spectrum. This was direct, unambiguous evidence that Titan possessed a substantial atmosphere containing significant quantities of methane. Kuiper's discovery was remarkable for several reasons. First, it confirmed that Titan was indeed the only moon in the solar system known to have a significant atmosphere. Second, it immediately raised profound questions about what else might be present in that atmosphere and what conditions might prevail on the surface below. Methane is a colorless, odorless gas at Earth temperatures, but at the frigid temperatures expected on a world so far from the sun, methane might behave very differently. Scientists began to speculate about whether Titan might have oceans or lakes of liquid hydrocarbons, though at the time there was no way to confirm such hypotheses. The methane discovery also raised a puzzle that persists to this day. Methane in an atmosphere exposed to ultraviolet radiation from the sun is not stable over geological timescales. Solar ultraviolet light breaks apart methane molecules, and the resulting molecular fragments recombine into more complex hydrocarbons like ethane and acetylene, or combine with atmospheric nitrogen to form even more exotic compounds. Over roughly 10 million years, all the methane in an atmosphere should be converted into these other products. Yet Titan clearly still has abundant methane. This means either that we happen to be observing Titan during a relatively brief geological moment when methane was recently released, or more likely that there is some ongoing source of methane replenishing the atmosphere from below. That source and its implications for Titan's internal structure and potential habitability would become one of the central mysteries driving exploration of this enigmatic world. For decades after Kuiper's discovery, Titan remained tantalizingly out of reach. Ground-based telescopes could detect the presence of methane and eventually other atmospheric gases, and they could make increasingly precise measurements of Titan's size, mass, and orbital characteristics. But the thick atmosphere that made Titan so interesting also made it impossible to see the surface. Whatever lay beneath that orange haze remained completely hidden from view. Some scientists proposed that Titan might be entirely covered by a global ocean of liquid hydrocarbons, a sea of methane and ethane hundreds of meters deep. Others suggested a surface of frozen ices, perhaps covered with organic sediments, raining down from the atmosphere. Without sending spacecraft to Saturn, there was simply no way to know. The space age began to change our understanding of the outer solar system in the late 1970s. Pioneer 11, launched in 1973, became the first spacecraft to fly through the Saturn system on September 1st, 1979. As it passed through, Pioneer 11 confirmed earlier estimates of Titan's temperature and mass. The surface temperature was measured at approximately 93 Kelvin, or minus 180 degrees Celsius, far colder than any temperature ever recorded on Earth. This extreme cold meant that water ice on Titan would be as hard as rock on Earth, while other substances that exist as gases or liquids on our planet would be frozen solid. Pioneer 11 also detected hints of a bluish haze in Titan's upper atmosphere, a finding that intrigued scientists and suggested more complex atmospheric phenomena than simple methane absorption. But the real revolution in our understanding of Titan came with the Voyager missions. Voyager 1 and Voyager 2 were twin spacecraft launched in 1977, designed to take advantage of a rare planetary alignment that would allow them to visit Jupiter, Saturn, Uranus, and Neptune in a grand tour of the outer solar system. Voyager 1's trajectory was specifically designed to provide an optimized flyby of Titan, reflecting the enormous scientific interest in this mysterious moon. When Voyager 1 swept past Titan in November 1980, passing within about 6,500 kilometers of the surface, scientists eagerly awaited the first close-up images of this long-hidden world. What they saw was simultaneously illuminating and frustrating. The images revealed not a clear view of the surface, but rather an unbroken orange sphere, completely shrouded in atmospheric haze. Titan's atmosphere was so thick, so filled with suspended organic particles, that visible light could not penetrate to the surface. The cameras on Voyager 1, designed to take stunning photographs across the visible spectrum, could reveal nothing of what lay beneath. However, Voyager 1 did return a wealth of other data. Its instruments measured Titan's atmosphere with unprecedented precision, determining that it was primarily composed of molecular nitrogen, not methane as some had expected. Nitrogen made up roughly 95% of the atmosphere, with methane comprising most of the remaining few percent. This meant Titan's atmosphere was fundamentally similar to Earth's in its primary composition, since Earth's atmosphere is also about 78% nitrogen. The main difference was the second most abundant gas, oxygen on Earth versus methane on Titan, a distinction with profound implications for chemistry and potential life. Voyager 1 also revealed that Titan's atmosphere extended to remarkable heights. The haze layers reached hundreds of kilometers above the surface, with a distinct detached haze layer visible in the upper atmosphere that gave Titan a unique appearance, unlike any other body in the solar system. The spacecraft's instruments detected traces of many other organic compounds in the atmosphere, including ethane, acetylene, propane, hydrogen cyanide, and various nitrogen-containing molecules. This chemical complexity suggested that Titan's atmosphere was a vast natural laboratory for organic chemistry, continuously producing new and potentially significant compounds through reactions driven by solar ultraviolet radiation. Despite the inability to see the surface, Voyager 1's radio occultation experiments provided crucial information about conditions near Titan's ground. As the spacecraft passed behind Titan as seen from Earth, radio signals transmitted through the lower atmosphere allowed scientists to determine temperature and pressure profiles with considerable precision. They found that the surface pressure was approximately 1.5 bar, meaning about 50% higher than Earth's surface pressure at sea level. The surface temperature was confirmed at around 94 Kelvin. And intriguingly, the temperature profile through the lower atmosphere suggested that conditions near the surface might allow methane to exist as a liquid, raising anew the possibility of methane seas or lakes. Voyager 2, which passed through the Saturn system in August 1981, provided additional data, but did not make a close Titan flyby. Its trajectory had been designed to continue on to Uranus and Neptune, a path that precluded the type of close encounter Voyager 1 had achieved. Still, the combined results from the two Voyager spacecraft transformed Titan from a point of light with an atmosphere into a complex world, crying out for further exploration. The decade following the Voyager encounters saw continued study of Titan from Earth-based observatories, with increasingly sophisticated instruments allowing new discoveries despite the immense distance. Infrared observations could penetrate the haze at certain wavelengths, providing hints of surface features. In 1994, the Hubble Space Telescope took images of Titan using specific infrared filters that could see through the orange murk, revealing for the first time that Titan's surface was not uniform. Large, bright, and dark regions were visible, including a continent-sized bright area that would later be named Xanadu. These observations confirmed that Titan had actual surface geology, not just a featureless expanse of liquid or ice, but they could not resolve what that geology actually looked like. The tantalizing glimpses provided by Hubble only deepened the mystery and strengthened the scientific case for a dedicated mission to Saturn and Titan. Such a mission had been under discussion since before the Voyager encounters, and by the early 1990s, NASA and the European Space Agency had committed to an ambitious joint project that would become one of the most successful planetary exploration missions in history. That mission was Cassini-Huygens, and it would finally reveal what Titan had been hiding beneath its orange clouds. The Cassini-Huygens mission represented one of the most complex and ambitious planetary exploration projects ever undertaken. It consisted of two main components: the Cassini orbiter, built by NASA, and the Huygens probe, built by the European Space Agency. The Italian Space Agency also contributed key hardware, including the orbiter's high-gain antenna. Together, these spacecraft would travel to Saturn, enter orbit around the ringed planet, and conduct years of detailed study of Saturn, its rings, and its moons, with particular emphasis on Titan. The combined spacecraft was massive by the standards of interplanetary probes, weighing approximately 5,700 kilograms at launch. The Cassini orbiter alone carried 12 sophisticated science instruments designed to study Saturn and its moons across multiple wavelengths of light, and through various physical measurements. Of particular importance for Titan exploration was the synthetic aperture radar system, which could penetrate the Moon's atmospheric haze and map surface features using radio waves. The Huygens probe, much smaller at about 350 kilograms, carried 6 instruments designed to study Titan's atmosphere during descent and to investigate whatever surface conditions it might encounter upon landing. On October 15, 1997, Cassini-Huygens launched from Cape Canaveral Air Force Station in Florida, atop a Titan 4B/Centaur rocket, the most powerful expendable launch vehicle available to NASA at the time. Even with this mighty rocket, the spacecraft did not have enough velocity to reach Saturn directly. Instead, it embarked on a 7-year voyage that included 4 gravity assist maneuvers, using the gravitational pull of Venus twice, Earth once, and Jupiter once, to gain the additional speed needed to reach the outer solar system. It was a cosmic billiard shot of extraordinary precision, threading the spacecraft through the inner solar system and then flinging it outward toward Saturn. The years of cruise were not idle time. Scientists used the spacecraft's instruments to study the interplanetary environment and to conduct observations during each planetary flyby. The joint flyby with Galileo at Jupiter in late 2000 produced unique 2 spacecraft observations of the giant planet. Finally, on July 1, 2004, after nearly 7 years of travel, Cassini fired its main engine for 96 minutes and became the first spacecraft ever to enter orbit around Saturn. Almost immediately, Cassini began observing Titan, flying close to the Moon on a carefully planned series of encounters that would ultimately number more than 120 targeted flybys over the course of the mission. Each close approach brought new radar images of the surface, new measurements of the atmosphere, new discoveries about this extraordinary world. But the climax of Titan exploration was still to come. On December 25, 2004, Christmas Day, the Huygens probe separated from the Cassini orbiter and began a 3-week coast toward Titan, setting up for what would become the most distant landing ever achieved by a spacecraft from Earth. On January 14, 2005, Huygens entered Titan's atmosphere at approximately 10:13 Universal Time, traveling at roughly 6 kilometers per second. The atmosphere began to slow the probe almost immediately, and the heat generated by this deceleration was absorbed by the probe's heat shield. About 4 minutes after entering the atmosphere, at an altitude of approximately 160 kilometers, Huygens deployed its pilot parachute, which pulled away the heat shield's back cover, and then deployed the main parachute, a canopy 8.5 meters in diameter. The descent had truly begun. For the next 2 hours and 27 minutes, Huygens drifted downward through Titan's thick atmosphere, its instruments working continuously, gathering data of incalculable scientific value. The probe measured temperature, pressure, and wind speed at every altitude. It analyzed the chemical composition of the atmosphere, detecting dozens of different organic compounds. Its cameras captured hundreds of images of the surface below, revealing a landscape that was at once eerily familiar and profoundly alien. What the descent cameras showed was remarkable. At high altitudes, the view was dominated by the orange haze, but as Huygens dropped lower, surface features began to emerge through the murk, The probe recorded what appeared to be drainage channels carved by flowing liquid into the bright terrain below. These channels converged toward darker regions that resembled coastlines, complete with what seemed to be river deltas spreading out onto darker plains. The overall impression was of a landscape shaped by flowing liquid, much as terrestrial landscapes are shaped by water. But on Titan, the liquid was not water. It was methane, or perhaps a mixture of methane and ethane, flowing at temperatures nearly 200 degrees below 0 Celsius. At 11:38 Universal Time, after a descent lasting nearly 2.5 hours, Huygens touched down on Titan's surface, becoming the first and still the only spacecraft ever to land on a body in the outer solar system, and the most distant landing from Earth ever achieved by human technology. The landing was remarkably gentle, with the probe impacting at a velocity of only about 4.5 meters per second, roughly equivalent to a person jumping off a chair. Huygens came to rest on a surface that initial analysis suggested was neither entirely solid nor entirely liquid, but perhaps a thin crust over a softer substrate, possibly wet with liquid hydrocarbons. The probe's cameras immediately began transmitting images of the landing site, providing humanity's first direct view of the surface of an outer solar system moon. What they revealed was a plain strewn with rounded pebbles and cobbles, resembling water-smoothed rocks on an Earth riverbed. But these were not rocks in any terrestrial sense. They were chunks of water ice, as hard as stone, at Titan's frigid temperatures. The sky above was a deep orange, and the surface was illuminated by weak sunlight, filtering through the thick atmosphere, producing lighting conditions comparable to a dim twilight on Earth, roughly 1,000 times dimmer than full daylight, but still bright enough for the cameras to capture clear images. Huygens continued transmitting data for approximately 72 minutes after landing, far exceeding its design requirement of surviving for just a few minutes on the surface. The probe's batteries eventually expired, and the transmissions fell silent, but not before Huygens had rewritten our understanding of this remarkable world. Analysis of the data would continue for years, revealing details about Titan's surface composition, the structure of its lower atmosphere, and the complex chemistry occurring in the skies above. Meanwhile, the Cassini orbiter continued its mission, flying past Titan again and again over the following years, building up an increasingly complete picture of the moon's surface and atmosphere. The radar instrument mapped vast regions, revealing not just drainage channels, but entire river systems, not just possible coastlines, but actual seas and lakes of liquid hydrocarbons. The infrared instruments observed the surface at wavelengths that could penetrate the haze, confirming and extending the radar observations. The discovery of methane lakes and seas, first announced in 2007, was one of the most significant findings of the mission, confirming that Titan is the only known body in the solar system, besides Earth, to have stable bodies of liquid on its surface. Each of Cassini's 127 targeted Titan flybys brought new discoveries and refinements to our understanding. The spacecraft would typically approach within a few thousand kilometers of the surface, sometimes dipping to less than 1,000 kilometers during particularly close encounters. At these distances, the radar could achieve resolutions fine enough to distinguish features only a few hundred meters across, revealing details of river channels, lake shorelines, and geological structures that would otherwise remain invisible. The cumulative effect of all these observations was transformative. Before Cassini, Titan was fundamentally mysterious, its surface hidden behind an impenetrable veil of orange haze. After Cassini, we possessed detailed maps covering approximately 70% of the surface, catalogs of hundreds of lakes and 3 major seas, inventories of atmospheric chemical species, and measurements of seasonal and temporal changes occurring over the mission's 13 years in the Saturn system. The transition from ignorance to knowledge, accomplished through the patient accumulation of data from flyby after flyby, represents one of the great achievements of robotic exploration. The seasonal changes observed by Cassini were particularly illuminating. Titan's seasons are driven by Saturn's 29.5-year orbital period around the Sun, meaning that each season on Titan lasts approximately 7 Earth years. When Cassini arrived in 2004, it was southern summer on Titan, with the South Pole tilted toward the Sun. Over the course of the mission, the seasons shifted, passing through equinox in 2009 and moving toward northern summer, which began around 2017 as the mission was ending. Scientists had predicted that these seasonal changes would affect cloud patterns, lake levels, and atmospheric circulation. Clouds were expected to form preferentially over whichever hemisphere was experiencing summer, driven by enhanced evaporation from the polar seas. The observations confirmed some of these predictions while revealing unexpected complexity. Cloud activity did shift northward as summer approached in the northern hemisphere, but the detailed patterns of cloud formation and dissipation proved more variable and less predictable than simple models had suggested. Changes in lake levels were also detected, though interpreting these changes proved challenging. Ontario Lacus, the southern hemisphere's largest lake, appeared to shrink during the mission, consistent with evaporation during southern summer. Meanwhile, the northern seas appeared relatively stable, though some smaller northern lakes showed evidence of changing shorelines. Whether these changes reflect seasonal cycles, longer-term climate variations, or geological processes like drainage into underground reservoirs remains uncertain. The atmosphere itself showed seasonal evolution. The distribution of haze particles shifted as the circulation patterns changed with the seasons. A dramatic polar vortex was observed forming over the South Pole as winter approached in that hemisphere, concentrating certain chemical species in a swirling atmospheric structure reminiscent of similar features in Earth's stratosphere. Hydrogen cyanide and other nitriles were particularly concentrated in this vortex, reaching abundances far higher than anywhere else in Titan's atmosphere. Temperature variations with season were also measured. The stratosphere warmed in whichever hemisphere was receiving more direct sunlight, while the opposite hemisphere cooled. These temperature changes affected the chemistry occurring at different altitudes, with some reactions proceeding faster in the warmer regions and others being suppressed. The coupling between thermal, chemical, and dynamical processes in Titan's atmosphere proved to be complex, providing challenges for atmospheric modelers that continue to this day. Cassini also discovered that Titan's interior structure was more complicated than simple models had predicted. Gravity measurements during close flybys allowed scientists to map variations in the gravitational pull exerted by different regions of the Moon, revealing information about the internal distribution of mass. These measurements, combined with observations of how Titan's shape responded to tidal forces from Saturn, provided evidence that the Moon's interior included layers of different densities, and that a liquid layer, presumably the subsurface ocean, existed at depth. The question of whether Titan's rotation was synchronized with its orbit, or whether the outer shell rotated at a different rate from the interior, was addressed through careful tracking of surface features over multiple years. Scientists found that surface landmarks appeared to shift position slightly relative to the expected locations based on Titan's orbital period. This small but detectable shift indicated that the icy outer shell was not rigidly connected to the interior, but was instead sliding over an underlying liquid layer, providing additional evidence for the subsurface ocean. The final years of the Cassini mission included several particularly ambitious observations. The spacecraft's orbit was adjusted to enable close flybys of Titan's polar regions, areas that had been less thoroughly mapped during earlier mission phases. These polar flybys provided the most detailed views yet of the northern seas and surrounding terrain, revealing shoreline features, coastal morphology, and evidence for waves and currents in the liquid surfaces. On September 15, 2017, after 20 years in space and 13 years orbiting Saturn, Cassini was deliberately plunged into Saturn's atmosphere. This dramatic end was chosen to prevent any possibility of the spacecraft eventually crashing into one of Saturn's potentially habitable moons and contaminating it with terrestrial microorganisms. By that point, Cassini had completed 293 orbits of Saturn and made 127 close flybys of Titan, along with numerous encounters with other Saturnian moons. As Cassini entered Saturn's atmosphere and transmitted its final data to Earth, it marked the end of an era of Saturn exploration that had fundamentally changed our understanding of that magnificent planetary system. The mission had been spectacularly successful, revealing Titan to be one of the most Earth-like and potentially habitable worlds in the solar system. But to truly appreciate what Cassini and Huygens revealed, we need to examine Titan's features in detail, starting with its remarkable atmosphere. Titan's atmosphere is unlike anything else in our solar system, except, in certain ways, our own planet's atmosphere. This comparison is not mere hyperbole. When scientists describe Titan as the most Earth-like body in the solar system, they are largely referring to atmospheric similarities that run surprisingly deep despite the enormous differences in temperature and distance from the Sun. The primary component of Titan's atmosphere is molecular nitrogen, which makes up approximately 94 to 98% of the total atmospheric mass, depending on altitude. On Earth, nitrogen comprises about 78% of our atmosphere. The similarity is striking and significant. Nitrogen is a relatively heavy molecule compared to lighter gases like hydrogen and helium, which means it tends to be retained by gravitational fields rather than escaping into space. Both Earth and Titan have sufficient gravity and sufficiently cool upper atmospheres to retain nitrogen over geological timescales, while smaller and warmer bodies like Mars have lost most of whatever nitrogen they once possessed. After nitrogen, the most abundant gas in Titan's atmosphere is methane, comprising roughly 5% near the surface, but decreasing to about 1.4% in the stratosphere. Methane plays a role on Titan somewhat analogous to water vapor on Earth. It can exist as both a gas and a liquid, under Titan's surface conditions, and it cycles between these phases through evaporation from surface liquids, transport through the atmosphere, condensation into clouds, and precipitation as rain that falls back to the surface. This methane cycle is the hydrocarbon equivalent of Earth's water cycle, and it drives much of the weather and geological activity observed on Titan. Hydrogen is the third most abundant atmospheric gas, present at roughly 0.1 to 0.2%. Various other hydrocarbons and nitrogen-containing compounds are present in trace amounts, many of them produced by photochemical reactions in the upper atmosphere. These include ethane, acetylene, propane, diacetylene, methylacetylene, hydrogen cyanide, cyanoacetylene, and many others. The diversity of organic compounds detected in Titan's atmosphere has led scientists to describe it as a chemical wonderland, a natural laboratory where complex organic chemistry proceeds continuously on a planetary scale. The atmospheric pressure at Titan's surface is approximately 1.47 bars, or about 1.5 times Earth's sea level pressure. This is the highest surface pressure of any solid body in the solar system after Earth itself. If you could stand on Titan's surface, you would feel noticeably more air pressing against you than anywhere on Earth, even at the lowest points in Death Valley or along the shores of the Dead Sea. This substantial pressure is one of the factors that makes Titan's atmosphere so different from the thin wisps surrounding other moons. The atmospheric temperature on Titan varies with altitude in a complex profile. At the surface, temperatures average around 93 to 94 Kelvin, or approximately minus 179 degrees Celsius. This is cold enough that water ice behaves like rock. Methane can exist as a liquid, and many substances that are gases at Earth temperatures become frozen solids. The temperature decreases with increasing altitude through the troposphere, the lowest atmospheric layer, reaching a minimum of about 70 Kelvin at the tropopause, approximately 44 kilometers above the surface. Above this point, in the stratosphere, temperatures actually increase with altitude due to the absorption of solar ultraviolet radiation by atmospheric haze particles. Speaking of haze, the orange color that has defined Titan's appearance since the first telescope observations is caused by suspended organic particles in the atmosphere, collectively known as tholins. This term was coined by the astronomer Carl Sagan and his colleague Bishun Khare in the 1970s to describe the complex organic materials produced when energy sources like ultraviolet light or electrical discharges act upon mixtures of nitrogen and simple hydrocarbons like methane. Tholins are not a single chemical compound, but rather a heterogeneous mixture of thousands of different organic molecules, ranging from small fragments to complex polymers, with molecular weights in the thousands. The process that creates tholins in Titan's atmosphere begins when solar ultraviolet radiation strikes nitrogen and methane molecules high in the stratosphere and mesosphere. This radiation is energetic enough to break molecular bonds, splitting nitrogen molecules into individual atoms and breaking apart methane into various fragments. These reactive species then recombine in myriad different ways, forming new and more complex molecules. Hydrogen cyanide, acetylene, ethane, and countless other compounds are produced through these photochemical reactions. Some of these products continue to react with each other, building up ever larger and more complex molecular structures. Eventually, these large organic molecules begin to stick together, forming tiny aerosol particles that gradually grow as they accumulate additional material. These particles are the tholins, and they are responsible for Titan's orange appearance. They absorb blue and ultraviolet light preferentially, while scattering and transmitting longer wavelengths like red and orange light, giving the atmosphere its distinctive color. The tholin particles are small, typically between 50 and 500 nanometers in diameter, but they are present in such enormous quantities that they completely obscure Titan's surface at visible wavelengths. As tholin particles grow and age, they slowly settle downward through the atmosphere, a process that takes years or even decades. Eventually, they reach the surface, depositing a continuous rain of organic material onto Titan's ground. Over the billions of years since Titan formed, this organic fallout has accumulated to substantial depths. Scientists estimate that the equivalent of a layer tens to hundreds of meters thick may have accumulated, forming the dune fields and organic sediments that cover much of Titan's equatorial regions. The implications of this organic chemistry are profound. The compounds being produced in Titan's atmosphere include many of the same building blocks that are thought to have been important for the origin of life on Earth. Amino acids, the components of proteins, have been detected in laboratory experiments that simulate Titan atmospheric chemistry. When tholins are exposed to liquid water, they can hydrolyze to produce these biologically relevant molecules. On a world with both abundant organic material and the periodic presence of liquid water, whether through cryovolcanic activity, impact melting, or contact with a subsurface ocean, the stage would seem to be set for at least the beginnings of prebiotic chemistry. The comparison to early Earth is instructive. Scientists believe that Earth's atmosphere before the rise of oxygen-producing life was quite different from today's atmosphere. It may have contained more methane, more ammonia, more hydrogen, and little or no free oxygen. The famous Miller-Urey experiment of 1953 showed that electrical discharges in a mixture of gases believed to represent the early Earth atmosphere could produce amino acids and other organic compounds. The same basic chemistry appears to be occurring continuously in Titan's atmosphere, driven not by lightning, but by solar ultraviolet radiation and energetic particles from Saturn's magnetosphere. In a sense, Titan can be viewed as a frozen snapshot of what early Earth might have looked like before life transformed our planet's chemistry. The organic compounds raining down onto Titan's surface are not being consumed by living organisms, not being oxidized by atmospheric oxygen, not being broken down by the biological processes that dominate organic chemistry on modern Earth. Instead, they accumulate, potentially preserving a record of prebiotic chemistry that has been erased on our own world by billions of years of biological activity. Studying Titan may thus provide insights not only into the potential for life on that world, but also into the chemical conditions that preceded life's origin on Earth. The methane in Titan's atmosphere deserves special attention because of its role in the moon's weather and climate. Methane near Titan's surface can exist in equilibrium between liquid and gaseous phases, much like water near Earth's surface. When temperatures rise, or the air becomes less saturated with methane vapor, liquid methane evaporates from surface lakes and seas. This vapor rises through the atmosphere, carried by convection and atmospheric circulation. At higher, colder altitudes, the methane vapor condenses, forming clouds. Titan's clouds are not like the white, fluffy water clouds of Earth. They are composed of tiny droplets of liquid methane, and they appear darker against the orange background of the atmospheric haze. Cloud activity on Titan varies with the seasons, which are driven by Saturn's 29.5-year orbit around the Sun. As different hemispheres receive more direct sunlight, warming occurs, evaporation increases, and cloud formation becomes more prevalent. During the northern summer, which began around 2017, scientists expected to see increased cloud activity over the northern hemisphere, where most of Titan's lakes and seas are located. When clouds become sufficiently saturated, precipitation occurs. It rains methane on Titan. This is not a theoretical prediction, but an observed fact, confirmed by both orbital observations and evidence from the Huygens landing site. The Huygens probe descended through what appeared to be a recent rain event, and the surface images suggested that liquid had been present in the immediate vicinity shortly before landing. Cassini observations detected cloud outbursts and tracked apparent rainfall events over the course of its mission. The rate of rainfall on Titan is much lower than on Earth, but individual rainstorms may be quite intense when they do occur. Models suggest that rainfall might happen only once every few hundred years in some regions, but when it does rain, the precipitation might be torrential. Large raindrops, slowed by Titan's thick atmosphere and weak gravity, would fall gently to the surface, feeding the river systems that carve channels across the landscape. These rivers are among the most striking features revealed by Cassini's radar mapping. Drainage networks extending for hundreds of kilometers have been identified, with tributary channels converging into larger streams that ultimately empty into the polar seas or infiltrate into the porous ground. The river channels are typically only visible to radar, appearing as dark linear features against the lighter surrounding terrain. Their morphology closely resembles terrestrial river systems, with dendritic drainage patterns, meandering channels, and braided stream features that all speak to the erosive power of flowing liquid. But it is the lakes and seas of Titan that most dramatically demonstrate the Moon's Earth-like character. These bodies of liquid hydrocarbons were first detected by Cassini in 2004 and 2005, appearing as dark patches in radar images of the polar regions. By the end of the mission, Cassini had mapped hundreds of individual lakes and 3 major seas, all concentrated in the northern hemisphere, with only a single small lake detected in the south. The largest of Titan's seas is Kraken Mare, named after the legendary sea monster of Norse mythology. Kraken Mare covers an area larger than the Caspian Sea on Earth, stretching approximately 1,170 kilometers from end to end. It contains an estimated 80% of all the surface liquids on Titan, making it by far the dominant reservoir in the Moon's hydrocarbon cycle. Radar sounding by Cassini revealed that Kraken Mare is remarkably deep, with areas where the radar signal could not detect the bottom, suggesting depths of at least 100 meters and potentially exceeding 300 meters. The second largest sea is Ligaea Mare, nearly heart-shaped and located closer to the North Pole. Ligaea Mare was studied in particular detail by Cassini, which made radar sounding passes that successfully detected bottom echoes. These measurements revealed depths reaching 170 meters or more, with the deepest areas concentrated in the central regions. Analysis of the radar absorption through the liquid indicated that Ligaea Mare is composed primarily of methane, with lesser amounts of ethane and dissolved nitrogen, somewhat different from what had been expected based on atmospheric chemistry models. The third major sea, Punga Mare, is smaller than the other two, but still substantial, covering an area comparable to Lake Victoria in Africa. Like its larger neighbors, Punga Mare lies in the far northern latitudes and is connected to the others through narrow straits and channels. One such strait, known as Selden Fridum and nicknamed the Throat of Kraken, connects Kraken Mare to Ligaea Mare and may experience significant tidal currents as Saturn's gravitational pull raises and lowers the sea levels slightly during Titan's 16-day orbit. The composition of these seas has been a subject of considerable scientific interest. Early models predicted that ethane, produced continuously by atmospheric photochemistry and relatively non-volatile at Titan temperatures, would dominate the surface liquid inventory. But measurements have shown that methane is actually more abundant than expected, at least in some of the seas. The northern seas, fed by methane-rich rainfall and rivers draining from the surrounding terrain, appear to be methane-dominated, while measurements in other areas suggest higher ethane content. This compositional variation likely reflects differences in how recently different regions have received precipitation versus how much evaporation and ethane accumulation have occurred. Beyond the major seas, Cassini identified hundreds of smaller lakes scattered across Titan's northern polar region. Some of these are substantial bodies of liquid in their own right, while others are little more than small ponds filling depressions in the terrain. Many have sharp-edged boundaries, suggesting they fill steep-sided basins, possibly formed by dissolution of underlying material or by other geological processes. Some lakes appear to be drying up, with rampart-like features around their edges that may represent shorelines from earlier higher liquid levels. In the southern hemisphere, only one confirmed lake has been identified, Ontario Lacus, named for Lake Ontario on Earth. Ontario Lacus is relatively small compared to the northern seas, covering about 15,000 square kilometers, but it has been studied extensively because it was accessible to Cassini's instruments during the early years of the mission when southern summer conditions prevailed. Radar sounding revealed that Ontario Lacus is quite shallow, with depths of only a few meters in most areas. The scarcity of surface liquids in the south compared to the north remains somewhat puzzling, though it may reflect seasonal or longer-term cyclical changes in Titan's climate. The surface of Titan beyond the polar lake districts presents a fascinating variety of terrains and geological features. Cassini's radar penetrated the atmospheric haze to map approximately 70% of the surface at varying resolutions, revealing a world shaped by multiple geological processes, including erosion, deposition, volcanism, and possibly tectonics. The equatorial regions of Titan are dominated by vast fields of linear dunes, stretching for thousands of kilometers across the landscape. These dunes are composed not of silicate sand, like terrestrial dunes, but of organic particles that have settled out of the atmosphere, mixed with water ice grains and other materials. The individual dune ridges are typically 100 to 150 meters tall, 1 to 2 kilometers wide, and can extend for hundreds of kilometers without interruption. They are oriented primarily east to west, shaped by the prevailing winds in Titan's lower atmosphere. The total amount of organic material locked up in Titan's dune fields is staggering. Scientists estimate that the dunes contain several hundred times the total volume of Earth's proven oil reserves. This is not oil in the terrestrial sense, of course, but rather solid organic particles accumulated over billions of years of atmospheric chemistry. If this material could somehow be accessed and processed, it would represent an energy resource beyond anything available on Earth, though of course the practical challenges of exploiting resources on a world 1.4 billion kilometers away are currently insurmountable. Between the dune fields lie elevated regions of brighter terrain, including the continent-sized Xanadu region, first glimpsed by the Hubble Space Telescope. Radar images show that Xanadu and similar bright regions have complex, mountainous topography, with peaks rising several hundred meters above the surrounding plains. These highlands may represent the oldest surfaces on Titan, heavily eroded by billions of years of exposure to methane rain and river action. Some scientists have suggested that Xanadu might be composed primarily of exposed water ice bedrock, with the organic surface material stripped away by erosion to reveal the underlying icy crust. Cryovolcanism, the eruption of volatiles like water and ammonia rather than molten rock, has been proposed as an active process on Titan, though definitive evidence remains elusive. Several features identified in Cassini images have been interpreted as possible cryovolcanic constructs, including flow-like features and apparent calderas. If cryovolcanism does occur on Titan, it could have profound implications for the moon's habitability, providing a mechanism to bring water and other materials from the subsurface ocean to the surface, where they could interact with atmospheric organic compounds. The question of what lies beneath Titan's surface has been one of the most intriguing aspects of the moon's exploration. Even before Cassini arrived, theoretical models had suggested that Titan might harbor a subsurface ocean of liquid water beneath its icy outer shell. Such an ocean would arise from the same processes that create subsurface oceans on other icy moons, like Europa and Enceladus. Radioactive heating in the rocky core, combined with tidal heating from gravitational interactions, could keep the deep interior warm enough for water to remain liquid even in the frigid outer solar system. Evidence for Titan's subsurface ocean accumulated through several independent lines of observation during the Cassini mission. The most direct evidence came from tracking the moon's rotation and tidal response. Scientists noticed that surface features observed by radar appeared to shift position slightly over time, as if the outer shell of Titan were moving independently of the interior. This behavior would be expected if the ice shell were floating on a liquid layer, allowing it to slip and shift relative to the solid core beneath. Additional evidence came from measurements of how Titan's shape responds to Saturn's gravitational pull. As Titan orbits Saturn, the varying distance from the giant planet causes tidal flexing, stretching Titan slightly along the line toward Saturn and compressing it at right angles. By measuring how much Titan deforms in response to these tidal forces, scientists can infer the interior structure, the observed degree of Deformation is consistent with a solid ice shell floating on a liquid layer, not with a completely solid interior. Radio observations during Huygens' descent also provided hints of a buried ocean. The probe detected signals that appeared to reflect from interfaces within Titan's interior, consistent with a liquid layer at a depth of 55 to 80 kilometers below the surface. While these measurements were not definitive, they added to the accumulating evidence that Titan harbors significant amounts of subsurface liquid water. The picture of Titan's interior that has emerged from these observations involves multiple layers. At the center lies a rocky core, probably composed of hydrated silicate minerals similar to those found in certain types of meteorites. This core contains the radioactive elements that provide the heat keeping Titan's interior warm. Surrounding the core is a layer of high-pressure ice, water frozen into exotic crystal structures that only form under the immense pressures found deep within large, icy bodies. Above this high-pressure ice lies the subsurface ocean, a global layer of liquid water mixed with ammonia, and possibly other dissolved materials. The ammonia is important because it acts as an antifreeze, allowing water to remain liquid at temperatures as low as -97 degrees Celsius, far below the normal freezing point. Above the ocean sits Titan's outer ice shell, composed of ordinary water ice that is as hard as rock at Titan's temperatures. This shell is estimated to be somewhere between 50 and 100 kilometers thick, though recent research has complicated this picture considerably. A December 2024 study reanalyzing Cassini data suggested that rather than a thin ice shell over a global ocean, Titan's interior might be dominated by a thick layer of slushy, partially melted high-pressure ice. This could imply that what lies beneath Titan's surface is better described as distributed pockets of liquid within an icy matrix rather than a vast, uninterrupted ocean, though further observations will be needed to confirm this interpretation. The possibility that Titan's interior might be slushier than previously thought does not necessarily diminish its astrobiological interest. Pockets of liquid within the ice could still provide environments where chemistry and potentially biology might occur. The key questions become how accessible these environments are and whether they exchange materials with the organic-rich surface above. One way that subsurface water might reach Titan's surface is through cryovolcanism or through impact events. When a large asteroid or comet strikes Titan, the energy released can melt substantial quantities of surface ice, creating temporary pools of liquid water that persist for decades to thousands of years before freezing. During this time, atmospheric organic compounds could dissolve in the water, potentially driving the same kinds of prebiotic chemistry that may have led to life's origin on early Earth. Laboratory experiments have shown that when tholin-like materials are exposed to liquid water, they hydrolyze rapidly, producing amino acids and other biologically relevant molecules. Impact melting on Titan could thus provide episodic opportunities for organic chemistry to advance toward greater complexity. The interaction between Titan's organic-rich surface and any liquid water environments, whether in impact melt pools, cryovolcanic flows, or the subsurface ocean, lies at the heart of the Moon's astrobiological potential. Scientists have identified at least two distinct ways that life might conceivably exist on Titan, though both remain highly speculative at present. The first possibility involves life in the subsurface ocean. similar in concept to life in the subsurface oceans of Europa or Enceladus. If Titan's buried water is indeed in contact with a rocky core, as it would be in the traditional ocean model, then chemical energy might be available from water rock. Reactions. On Earth, chemosynthetic microorganisms thrive in deep-sea hydrothermal environments, deriving energy from reactions between water and hot rock without any dependence on sunlight. Similar life might conceivably exist in Titan's subsurface ocean, feeding on chemical energy and building cellular structures from dissolved organic compounds that seeped down from the surface. However, recent research has suggested that this scenario might be more challenging than previously assumed. A 2025 study led by researchers at the University of Arizona and Harvard University examined the potential for life to exist in Titan's subsurface ocean by focusing on a simple metabolic pathway: fermentation of glycine, the simplest amino acid. Fermentation is one of the most basic energy-yielding metabolisms known, operating without oxygen, and likely arising very early in Earth's history. The researchers reasoned that if any life exists in Titan's ocean, fermentation-based microorganisms would be among the most plausible candidates. The researchers developed bioenergetic models to estimate how much organic material might be available to support such life. What they found was that despite the enormous quantity of organic compounds present on Titan's surface, only a small fraction appears capable of reaching the subsurface ocean through known transport mechanisms. Meteorite impacts can create melt pools that allow surface organics to percolate downward. But based on what we can determine from current models, this process appears limited. The implication is that any microbial biosphere in Titan's ocean would likely be extremely sparse, making detection extraordinarily difficult, even for future missions that could somehow sample the ocean directly. The second, more exotic possibility for Titanian life involves organisms that might live not in water, but in the liquid hydrocarbons that cover portions of the surface. This would represent a form of life fundamentally unlike anything on Earth, using methane or ethane as a solvent instead of water, and employing entirely different chemistry for energy metabolism and cellular structure. Such life remains purely hypothetical, but scientists have explored what it might look like. In 2015, researchers at Cornell University proposed a theoretical cell membrane that could potentially function in liquid methane at cryogenic temperatures. They called this structure an azotosome, from the Greek words for nitrogen and body, because it would be composed of small nitrogen-containing organic molecules, rather than the phospholipids that form cell membranes on Earth. Their computer simulations suggested that azotosomes could theoretically self-assemble under Titan surface conditions and would have properties surprisingly similar to terrestrial cell membranes, including flexibility, stability, and the ability to form enclosed vesicles. However, subsequent research has cast doubt on whether azotosomes could actually form under realistic Titan conditions. A 2020 study by researchers at Chalmers University of Technology in Sweden examined the thermodynamics of azotosome formation and found significant barriers. Their quantum mechanical calculations suggest that the molecules proposed for azotosome construction would preferentially form crystalline structures rather than assembling into membranes. This doesn't rule out methane-based life on Titan entirely, but it does suggest that such life would need to rely on different cellular architectures than those proposed so far. The possibility of life on Titan, whether in the subsurface ocean or the surface hydrocarbon lakes, has motivated continued interest in exploring this fascinating world. The Cassini-Huygens mission provided an enormous amount of data, but many questions remain unanswered. What is the exact structure of Titan's interior? How much exchange occurs between a surface and the subsurface ocean? What organic compounds are present on the surface, and how complex have they become? Are there any signs of current geological or biological activity? To address these questions, NASA has approved a new mission to Titan that will take exploration to an entirely new level. That mission is called Dragonfly, and it represents one of the most ambitious planetary exploration concepts ever attempted. Dragonfly is a rotorcraft lander, essentially a car-sized drone that will fly through Titan's skies and make multiple landings at different locations across the moon's surface. The concept exploits Titan's unique combination of a thick atmosphere and low gravity, which together make powered flight far easier than on any other solid body in the solar system. Titan's atmospheric density is about 4 times that of Earth at sea level, while its surface gravity is only about 1/7 of Earth's. A vehicle that would struggle to lift off the ground on Earth can soar effortlessly through Titan's skies with relatively small rotors and modest power requirements. The Dragonfly spacecraft will be equipped with 8 rotors arranged in 4 pairs, giving it redundancy in case of mechanical problems. It will be powered not by solar panels, which would be nearly useless under Titan's perpetually overcast skies, but by a radioisotope thermoelectric generator, the same type of nuclear power source that has enabled long-duration missions to the outer solar system since the Pioneer and Voyager days. This power source will allow Dragonfly to recharge its batteries during the long Titan nights, each lasting about 8 Earth days, and then take flight during the daylight periods. The multi-mission radioisotope thermoelectric generator aboard Dragonfly will convert the heat from the radioactive decay of plutonium-238 into electrical power. This type of power system has been used on numerous deep space missions, including the Cassini orbiter itself, and has proven highly reliable over decades of operation. On Titan, where solar power is impractical due to the combination of distance from the sun and atmospheric absorption, nuclear power is essentially the only viable option for a long-duration surface mission. The scientific instruments aboard Dragonfly have been carefully selected to address the key questions about Titan's chemistry and potential habitability. The Dragonfly mass spectrometer will identify the molecular composition of surface materials and atmospheric gases with high precision, searching for organic compounds, including potential biosignatures or prebiotic molecules. The instrument can detect compounds at very low concentrations, enabling the identification of trace species that might be of particular scientific interest. The Dragonfly gamma ray and neutron spectrometer will probe the composition of the surface materials to a depth of about 0.5 meter, providing information about the bulk chemical makeup of the terrain at each landing site. By measuring gamma rays and neutrons emitted when cosmic rays strike the surface, this instrument can determine the abundances of major elements without requiring direct sampling. A suite of cameras will provide visual documentation of the landing sites and flight paths. The Dragonfly camera suite includes forward-looking cameras for navigation and landing site assessment, downward-looking cameras for surface imaging during flight, and panoramic cameras for documenting the surroundings after landing. These images will not only serve scientific purposes, but will also provide humanity with its first extensive photographic documentation of Titan's surface since the single landing site photographed by Huygens in 2005. Geophysical and meteorological instruments will measure seismic activity, atmospheric conditions, and other environmental parameters. The DragMet package includes sensors for temperature, pressure, wind speed and direction, and atmospheric electricity. A seismometer will listen for vibrations in Titan's crust, potentially revealing information about the interior structure and any ongoing geological activity. These measurements will help scientists understand the physical environment of Titan in unprecedented detail. The mission is scheduled to launch in July 2028 and will take approximately 6 years to reach the Saturn system, arriving in 2034. After entering Titan's atmosphere, Dragonfly will descend using an aeroshell and parachutes, similar to the Huygens landing, but with the crucial difference that Dragonfly will not simply sit at its landing site. Instead, it will conduct a series of flights, each covering distances of several kilometers, allowing it to explore dozens of different locations over the course of its planned 3.3-year primary mission. Dragonfly's initial landing site will be in the Shangri-La Dune Field in Titan's equatorial region, not far from where Huygens landed in 2005. This area was chosen because the terrain is relatively flat and smooth, minimizing the risk during the initial landing and early operations. From there, Dragonfly will make flights of progressively greater distance, exploring the diverse geology of the equatorial region while working its way toward its ultimate destination, Selk Crater. Selk Crater is an impact crater approximately 80 kilometers in diameter, formed when an asteroid or comet struck Titan at some point in the geological past. The crater is of particular interest because impact events create conditions that may be favorable for prebiotic chemistry. When the impactor struck, it would have generated enormous heat, melting the ice in the immediate vicinity and creating a temporary pool of liquid water that might have persisted for centuries or even millennia before freezing. During this time, atmospheric organic compounds could have dissolved in the water, potentially driving chemical reactions that form amino acids and other biologically significant molecules. If any such products remain preserved in the crater, Dragonfly's instruments might be able to detect them. The scientific payload of Dragonfly includes a mass spectrometer designed to identify the molecular composition of surface and atmospheric samples with high precision. This instrument will search for complex, organic molecules, including potential biosignatures or prebiotic compounds that might indicate the chemistry has progressed toward life. Dragonfly will also carry cameras for imaging, sensors to measure meteorological conditions, and instruments to investigate the moon's seismic activity and internal structure. One of the most exciting aspects of Dragonfly is its ability to perform powered flight on another world. While the Ingenuity helicopter on Mars demonstrated the flight is possible in an extraterrestrial atmosphere, Titan's thick atmosphere and low gravity make it an even more hospitable environment for aerial exploration. Dragonfly will be able to fly for periods of up to an hour at a time, covering distances of 8 kilometers or more in a single flight. Over the course of the mission, it may travel more than 175 kilometers in total, exploring more terrain than all previous Mars rovers combined. The flight capability also allows Dragonfly to access locations that would be impossible for a wheeled rover, such as the interiors of craters, the tops of dunes, or areas separated from the landing site by impassable terrain. Each flight will be carefully planned based on reconnaissance imaging, and the data returned will inform scientists about Titan's geology, chemistry, and potential habitability in ways that no previous mission could achieve. Beyond Dragonfly, scientists have proposed even more ambitious concepts for future Titan exploration. One of the most striking is a submarine that would explore the depths of Kraken Mare, diving to the bottom of Titan's largest sea and investigating its composition, temperature, currents, and any signs of geological or biological activity. NASA has studied this concept in preliminary phases, though it remains far from approval or funding. Such a mission would face extraordinary challenges, including the need to communicate through a thick atmosphere and liquid layer, operate autonomously for extended periods, and survive the extreme cold and chemical environment of a hydrocarbon sea. Other concepts include balloon-borne instruments that would float through Titan's atmosphere for extended periods, studying the weather, chemistry, and cloud formation processes from within. An aircraft that could fly indefinitely through Titan's skies, sustained by the low gravity and thick atmosphere, might map the entire surface in detail impossible from orbit. Each of these concepts remains speculative for now, but they illustrate the enduring scientific interest in this remarkable world and the potential for future discoveries. As we look toward the future of Titan exploration, it is worth reflecting on what we have learned and what questions remain. Titan is a world of profound complexity, a place where familiar processes like rain, rivers, and lakes occur with utterly unfamiliar materials under utterly unfamiliar conditions. Its thick atmosphere shields the surface from the harshness of space, while continuously producing organic compounds of astonishing variety. Its subsurface may harbor a global ocean of liquid water, though recent research suggests a more complicated interior structure than previously assumed. Its surface features show the unmistakable signs of active geology, with erosion, deposition, and possibly volcanism, shaping the landscape over geological time. Whether life exists on Titan remains an open question that we cannot yet answer. The conditions appear potentially favorable, at least in some environments. Liquid water seems likely to be present in the subsurface based on multiple lines of evidence, and organic compounds are available in extraordinary abundance on the surface. Energy sources exist in the form of chemical reactions and possibly geothermal heat. All the basic requirements for life as we know it appear to be present, though in configurations very different from Earth's. But life on Titan, if it exists, would likely be extremely sparse and difficult to detect based on current modeling. The recent studies suggesting limited organic transport to the subsurface ocean paint a picture of a potential biosphere that might contain only tiny populations of microorganisms scattered across a vast dark sea. Finding such life would require either extraordinary luck or missions far more capable than anything yet built, and life based on hydrocarbon solvents rather than water remains entirely theoretical, with fundamental questions about whether such biochemistry is even possible remaining unanswered. What seems certain is that Titan will continue to captivate scientists and the public alike for generations to come. It offers a window into planetary processes that we cannot study anywhere else, a natural laboratory for organic chemistry that has been running experiments for billions of years, and perhaps the best chance we have of discovering life in our solar system that arose independently from life on Earth. The answers to the questions Titan raises may ultimately tell us something profound about the nature of life itself and about our place in a cosmos that may be far more alive than we ever imagined. As you contemplate these mysteries, perhaps on a clear night you might look toward the constellation where Saturn currently resides and imagine that distant world, its orange haze glowing softly in the weak sunlight, its methane seas rippling under alien skies, its hidden ocean stirring in eternal darkness. Titan is out there right now, continuing to evolve, continuing to process organic chemistry on a planetary scale, perhaps continuing to harbor secrets we have not yet begun to guess. The light reaching your eyes left Saturn more than an hour ago. So even as you observe the present, you are seeing the past. By the time Dragonfly arrives in 2034, Titan will have experienced another decade of seasons, another decade of methane rain and tholin accumulation, another decade of whatever processes shape that remarkable world. We will be watching, waiting to learn what new discoveries await. Thank you for joining me on this journey to Saturn's largest moon. If you found this exploration meaningful, please consider liking and subscribing to the channel. Your support helps me continue making these deep explorations of space and the profound questions they raise about life, the universe, and our place within it. Until next time, keep looking up at the night sky and wondering what secrets the cosmos still holds. Titan awaits, shrouded in orange haze, hiding mysteries we are only beginning to unravel. And somewhere out there, perhaps on that distant frozen world, the answer to one of humanity's oldest questions may be waiting to be found. Are we alone? Titan may one day help us answer that question. And whatever the answer turns out to be, it will change everything we thought we knew about life, about the universe, and about ourselves. Good night, and may your dreams carry you across the billion kilometers of space to that enigmatic moon where rivers of methane flow through mountains of ice, where organic snow falls from orange skies, and where the possibility of alien life still beckons from beneath the frozen surface. Sleep well, knowing that the universe is stranger, more beautiful, and more full of possibility than we can possibly imagine. And remember, Titan is out there, waiting for us, keeping its secrets for just a little while longer. Let us now delve deeper into the extraordinary world of tholins and the prebiotic chemistry that makes Titan such a compelling target in the search for life. The organic molecules produced in Titan's atmosphere represent one of the largest natural experiments in complex chemistry occurring anywhere in our solar system. And understanding these processes has implications far beyond the boundaries of this single moon. Tholins, as we have discussed, are complex organic materials produced when energy acts upon mixtures of nitrogen and simple carbon compounds like methane. The term itself comes from the Greek word tholos, meaning muddy or murky, a reference to the reddish-brown color of these materials when produced in laboratory settings. Carl Sagan and Bashun Kare coined this term in the 1970s when they began systematically studying the products of experiments designed to simulate Titan's atmospheric chemistry. The process begins in the uppermost reaches of Titan's atmosphere, where solar ultraviolet radiation possesses sufficient energy to break apart even the strong triple bond of molecular nitrogen and the covalent bonds within methane molecules. At altitudes above 1,000 kilometers, photons with wavelengths shorter than about 100 nanometers can dissociate nitrogen directly, producing reactive nitrogen atoms that immediately begin seeking bonding partners. Methane photolysis occurs somewhat lower in the atmosphere, typically between 200 and 1,000 kilometers altitude, where ultraviolet photons split methane into methyl radicals and hydrogen atoms. NASA's James Webb Space Telescope recently detected the methyl radical directly in Titan's atmosphere for the first time, providing crucial confirmation of this photochemical process. The methyl radical is a key intermediate in Titan's atmospheric chemistry, reacting rapidly with other molecules to form more complex hydrocarbons. When two methyl radicals collide and bond, they form ethane, the second most abundant hydrocarbon in Titan's atmosphere, after methane itself. When methyl radicals react with nitrogen atoms or nitrogen-containing species, they begin building the nitrogen-rich organic compounds that give tholins their distinctive properties. The cascade of reactions proceeding from these initial photolysis events is extraordinarily complex. Scientists have identified dozens of different compounds in Titan's atmosphere, ranging from simple two-carbon molecules like acetylene and ethylene to complex ring structures like benzene and larger aromatic compounds. Each of these molecules can participate in further reactions, building up ever more complex structures. The process resembles, in some ways, the polymerization reactions used in industrial chemistry to create plastics and other synthetic materials. Though on Titan, these reactions occur naturally, driven by solar energy over billions of years. One particularly significant class of compounds produced in Titan's atmosphere is the nitriles, molecules containing a carbon-nitrogen triple bond. Hydrogen cyanide was one of the first complex molecules detected in Titan's atmosphere, identified by Voyager 1's infrared spectrometer in 1980. Since then, many other nitriles have been detected, including cyanoacetylene, dicyanoacetylene, and acrylonitrile. These molecules are of special interest because nitriles are highly reactive and can serve as precursors to a wide range of biologically relevant compounds. Hydrogen cyanide, in particular, has been extensively studied in origin of life research as a potential building block for amino acids, nucleobases, and other molecules essential to life. Acrylonitrile deserves special attention because of its proposed role in forming cell-like structures on Titan. This molecule, composed of 3 carbon atoms, 3 hydrogen atoms, and 1 nitrogen atom arranged in a specific geometry, has properties that make it potentially capable of forming membrane-like structures in liquid methane. The azotosome concept, proposed by Cornell researchers in 2015, envisioned these molecules assembling into enclosed vesicles that could serve functions analogous to cell membranes on Earth, separating an interior chemical environment from the exterior liquid and potentially providing the structural basis for a rudimentary form of life. The laboratory synthesis of Titan tholin analogs has been an active area of research for several decades, producing materials that can be studied in detail to understand what might exist on the actual moon. These experiments typically involve exposing mixtures of nitrogen and methane to various energy sources, including ultraviolet radiation, electrical discharges, or energetic particle bombardment. The resulting brown or orange-red materials are collected and analyzed using sophisticated chemical techniques, revealing a complexity that continues to surprise researchers. When Titan tholins produced in laboratory settings are exposed to liquid water, they undergo hydrolysis reactions that produce a remarkable suite of prebiologically interesting compounds. Amino acids, the building blocks of proteins, form readily under these conditions. Studies have identified glycine, alanine, aspartic acid, and many other amino acids in hydrolyzed tholin samples. The amino acids produced are racemic, meaning they contain equal amounts of left-handed and right-handed molecular forms, as would be expected from non-biological chemical synthesis. On Earth, living organisms use almost exclusively left-handed amino acids, so finding racemic mixtures is actually an indicator of abiotic origin. Beyond amino acids, hydrolyzed tholins contain nucleobases, the molecular components that form the information-carrying portion of DNA and RNA. Adenine, guanine, cytosine, and uracil have all been detected in various tholin hydrolysis experiments. The presence of these molecules is remarkable because it suggests that the raw materials for genetic information storage could be produced naturally from simple atmospheric gases, given only energy and water. Whether such molecules could actually assemble into functional nucleic acids under Titan conditions is unknown, but their presence in tholins speaks to the chemical richness of this material. The connection between Titan tholin chemistry and the famous Miller-Urey experiment of 1953 is direct and illuminating. Stanley Miller and Harold Urey demonstrated that passing electrical discharges through a mixture of gases thought to represent Earth's early atmosphere, including methane, ammonia, hydrogen, and water vapor, produced amino acids and other organic compounds. Their experiment essentially created a tholin-like material under conditions simulating early Earth. The similarity between Miller-Urey products and Titan tholins suggests that the chemistry occurring on Titan today may be analogous to chemistry that occurred on Earth billions of years ago, before life emerged and transformed our planet's surface environment. Modern understanding of Earth's early atmosphere has evolved since Miller and Urey's time, with many scientists now believing that the early atmosphere was less reducing than Miller and Urey assumed, containing more carbon dioxide and less methane and ammonia. This has led some to question whether Miller-Urey chemistry was actually relevant to life's origin on Earth. However, even under more oxidizing atmospheric conditions, impact events and volcanic outgassing could have created locally reducing environments where similar chemistry might proceed. And regardless of Earth's early atmospheric composition, Titan provides a present-day example of an intensely reducing atmosphere where complex organic chemistry demonstrably occurs. The rate at which organic material accumulates on Titan's surface is substantial by geological standards. Scientists estimate that approximately 500 to 1,000 kilograms of tholin material settles out of the atmosphere every second, distributed across the entire surface of the moon. Over the 4.5 billion years since Titan formed, this continuous organic rain has deposited material to equivalent depths, ranging from tens of meters to potentially hundreds of meters, depending on assumptions about how the deposition rate has varied over time. Much of this material has been reworked by geological processes, concentrated in some areas and removed from others, but the total inventory of surface organics on Titan represents one of the largest reservoirs of abiotic organic material anywhere in the solar system. The dune fields of Titan's equatorial regions represent the most visible concentration of this organic material. Cassini's radar images revealed linear dunes covering vast areas, with individual dune ridges extending for hundreds of kilometers across the landscape. Spectroscopic measurements suggest that these dunes are composed primarily of organic particles, likely a mixture of different tholin-derived compounds modified by surface processing. The grains are probably fine, similar in size to sand grains on Earth, but composed of organic molecules rather than silicate minerals. Understanding how the dune material formed and evolved provides insight into Titan's long-term organic chemistry. The particles may represent directly deposited atmospheric tholins, or they may have undergone additional chemical processing on the surface. Exposure to cosmic rays, which penetrate to Titan's surface despite the thick atmosphere, could induce additional chemical reactions in surface organics. Interaction with any liquid water that might occasionally be present, whether from cryovolcanic flows or impact melting, could drive hydrolysis reactions, producing amino acids and other compounds. The surface organic layer on Titan is thus not merely a passive accumulation of atmospheric fallout, but potentially an active chemical system with its own evolutionary history. The interaction between Titan's surface organics and liquid water represents one of the most intriguing aspects of the Moon's potential habitability. On Earth, liquid water is essential for life, serving as the solvent in which biochemical reactions occur and the medium through which nutrients and waste products are transported. If liquid water occasionally becomes available on Titan's surface, even briefly, it could drive chemical reactions that are impossible in the cold, water-free normal environment. These reactions might produce more complex and potentially biologically relevant molecules than atmospheric photochemistry alone. Impact events represent the most dramatic source of temporary liquid water on Titan's surface. When a large asteroid or comet strikes an icy body, the kinetic energy of the impact is converted into heat, melting large quantities of ice in the immediate vicinity of the impact site. On Titan, where the surface ice is composed of water in its common crystalline form, such impacts would create pools or lakes of liquid water that might persist for considerable periods before refreezing. The lifetime of impact-generated water bodies on Titan depends on many factors, including the size of the impactor, the properties of the surrounding terrain, and whether the melt pool is covered by an insulating layer that slows heat loss. Models suggest that large impact craters might contain liquid water for periods ranging from centuries to tens of thousands of years. During this time, atmospheric organic compounds would dissolve in the water and undergo the same kinds of hydrolysis reactions studied in laboratory tholin experiments. The result would be a temporary crucible of prebiotic chemistry, a localized environment where the conditions necessary for life's emergence might briefly be satisfied. Selk crater, the ultimate destination of the Dragonfly mission, was chosen in part because it shows evidence of past water activity. The crater's morphology suggests that impact melting occurred when it formed, and the floor may preserve organic materials that interacted with liquid water during the warm period following impact. By sampling materials from Selk crater and comparing them to materials from the surrounding terrain that did not experience impact melting, Dragonfly scientists hope to understand how water interaction affects Titan's organic chemistry and whether the products include molecules of potential biological significance. Cryovolcanism represents another possible source of liquid water on Titan's surface, though definitive evidence for active cryovolcanism remains elusive. If water and ammonia from the subsurface ocean occasionally erupt onto the surface through volcanic-like processes, they would create flows of liquid that could interact with surface organics before freezing. Such eruptions might theoretically be driven by pressure buildup in the subsurface, by tidal heating effects, or by other geological processes not yet understood. Several features observed in Cassini images have been interpreted as potentially cryovolcanic, though alternative explanations exist. Sotra Patera, a feature in Titan's southern hemisphere, includes what appears to be a volcanic caldera with flow-like features extending from it. Based on its morphology, this could represent a site where water-based volcanism occurred at some point, creating conditions favorable for organic chemistry. The evidence remains circumstantial, and definitive confirmation of cryovolcanism on Titan awaits future observations. The question of whether methane-based life could exist on Titan's surface, independent of any water-based life in the subsurface ocean, remains one of the most speculative aspects of Titan astrobiology. Life as we know it requires a liquid solvent, and on Earth, that solvent is water. But water's special properties as a solvent arise from its molecular structure, particularly its ability to form hydrogen bonds and to dissolve a wide range of polar molecules. Other liquids with different properties might serve as solvents for different kinds of chemistry, potentially including chemistry complex enough to constitute life. Liquid methane and ethane, which fill Titan's lakes and seas, have very different properties from water. They are nonpolar solvents, meaning they do not dissolve the same kinds of molecules that water dissolves. The biochemistry of any life in these liquids would need to be completely different from terrestrial biochemistry, using different types of molecules for energy storage, structural support, and information processing. Whether such an alternative biochemistry is possible remains unknown, but scientists have begun to explore what it might look like. One constraint on hydrocarbon-based life is energy availability. On Earth, most life ultimately derives energy from sunlight, either directly through photosynthesis or indirectly by consuming organisms that photosynthesize. Some microorganisms obtain energy from chemical reactions that do not involve sunlight, but these chemosynthetic pathways still require specific combinations of oxidants and reductants that are not obviously available in Titan's hydrocarbon environment. The energy sources that might sustain methane-based life on Titan are not yet clear. Some researchers have proposed that life in Titan's methane seas might metabolize by combining hydrogen from the atmosphere with acetylene from the surface, producing methane as a waste product. This reaction is thermodynamically favorable under Titan conditions and would provide modest amounts of energy. Intriguingly, Cassini observations revealed that hydrogen near the surface appeared to be depleted at a higher rate than models predicted, and acetylene was less abundant on the surface than expected. These patterns are consistent with consumption by some surface process, though they could also be explained by atmospheric chemistry or surface interactions we don't fully understand. Most scientists lean toward non-biological explanations, but the observations remain intriguing. Even if methane-based life is theoretically possible, it would face enormous challenges. The low temperatures on Titan's surface, around minus 179 degrees Celsius, would slow all chemical reactions dramatically compared to Earth conditions. Life processes that take milliseconds at room temperature might take years or centuries at Titan temperatures. Whether natural selection could operate effectively under such conditions, producing organisms capable of evolution and adaptation, is entirely unknown. Methane-based life on Titan, if it exists, might be so slow and so sparse that detecting it would be extraordinarily difficult. The concept of life that we cannot recognize, because it is too different from terrestrial life, raises profound questions about the search for extraterrestrial life in general. When we design instruments to search for biosignatures on other worlds, we inevitably base those instruments on our understanding of life as it exists on Earth. If life on Titan or elsewhere uses fundamentally different chemistry, we might fail to recognize it, even if our instruments pass directly through a thriving alien ecosystem. This possibility argues for maintaining open minds and developing detection strategies that are as agnostic about the nature of life as possible. The Dragonfly mission incorporates this philosophy to some extent. While its mass spectrometer is designed to detect specific molecules of interest, it is also capable of characterizing a broad range of organic compounds without preconceptions about what should be present. If unexpected molecules appear in the data, scientists will have the capability to investigate them, potentially revealing chemistry that no one predicted. The combination of targeted searches for expected compounds and open-ended surveys for the unexpected gives Dragonfly the best chance of discovering whatever chemistry Titan has produced, whether biological or not. Looking beyond Dragonfly, the future exploration of Titan holds extraordinary promise. The scientific questions raised by this moon touch on some of the deepest issues in planetary science and astrobiology. How do complex organic molecules arise from simple precursors? Under what conditions can prebiotic chemistry progress toward life? Is water the only solvent that can support biochemistry, or are alternatives possible? What does the diversity of potentially habitable environments in our solar system tell us about the likelihood of life elsewhere in the universe? Each of these questions has implications far beyond Titan itself. Understanding organic chemistry on Titan helps us understand organic chemistry in all planetary atmospheres, including the atmospheres of exoplanets around other stars. If prebiotic chemistry can progress toward life under Titan's conditions, it might do so on countless similar worlds throughout the galaxy. And if life has actually arisen on Titan, independent of life on Earth, it would demonstrate that the origin of life is not a singular miracle, but a natural consequence of planetary processes that might occur wherever conditions allow. The James Webb Space Telescope is already contributing to Titan science, observing the moon at wavelengths that Cassini could not access, and providing new information about atmospheric chemistry and surface composition. Future ground-based telescopes with advanced adaptive optic systems will provide unprecedented views of Titan from Earth, potentially tracking seasonal changes and monitoring for geological activity. And after Dragonfly, additional missions might follow, each building on the knowledge gained by its predecessors. The submarine concept for exploring Kraken Mare remains one of the most audacious ideas in planetary exploration. Such a vehicle would need to operate autonomously for extended periods at the bottom of an alien sea, surviving temperatures nearly 200 degrees below zero in a liquid composed of hydrocarbons that would dissolve many common materials. Communication would require the vehicle to surface periodically or to relay data through acoustic links to a surface station. Yet the scientific return from such a mission would be immense, revealing the composition, currents, and geological features of a body of liquid utterly unlike any on Earth. Balloon-borne platforms floating through Titan's atmosphere represent another promising concept. A balloon filled with hydrogen or helium would float in Titan's dense atmosphere, much as similar balloons float on Earth, providing a stable platform for long-duration atmospheric studies. Such a platform could monitor weather patterns, track cloud formation and precipitation events, and sample the atmosphere at multiple altitudes over periods of months or years. Combined with surface observations from a landed vehicle like Dragonfly, balloon data would provide a comprehensive picture of Titan's atmospheric dynamics and chemistry. The technical challenges of these advanced missions are formidable, but not insurmountable. The distance to Saturn means that communication delays of over an hour each way are unavoidable, requiring any vehicle to operate with substantial autonomy. The cold temperatures demand heating systems or specially designed materials that can function in extreme cold. The radiation environment near Saturn, while less intense than near Jupiter, still poses challenges for electronic systems. Yet each of these challenges has been addressed successfully in previous missions, and there is no fundamental barrier to extending exploration of Titan, far beyond what Dragonfly will accomplish. As we contemplate the future of Titan exploration, it is worth reflecting on how far we have come since Christian Huygens first glimpsed a small point of light near Saturn nearly 4 centuries ago. That point of light has become a world of rivers and seas, of mountains and dunes, of organic chemistry, and perhaps of life itself. We have sent spacecraft across billions of kilometers to study this world, landed on its surface, and prepared to fly through its skies. Each step has revealed new wonders and posed new questions, drawing us deeper into the mystery of this extraordinary moon. Titan challenges us to think beyond the familiar, to imagine forms of chemistry and perhaps forms of life that differ fundamentally from anything we know. It reminds us that the universe is vaster and stranger than our limited experience on this one planet can encompass. And it offers the tantalizing possibility that somewhere beneath those orange clouds, in the darkness of a subsurface ocean or the strange environment of a methane sea, something might be alive, something that emerged from the same cosmic processes that produced us, but followed an entirely different path. The questions Titan raises are not merely scientific, but philosophical. What is life? How do we recognize it? Are we capable of understanding forms of existence profoundly different from our own? These questions have engaged human thought for millennia, but only now do we have the tools to seek empirical answers on other worlds. Titan is one of our best opportunities to find such answers, and the coming decades of exploration will bring us closer than ever before to the truth. Thank you once again for joining me on this journey through the mysteries of Saturn's largest moon. The universe has provided us with a world that seems almost designed to stimulate our curiosity and challenge our assumptions. Titan is out there, continuing its slow dance around Saturn, continuing its patient chemical evolution, perhaps continuing to harbor secrets that will one day transform our understanding of life itself. Keep wondering, keep exploring, and keep looking up at the stars, knowing that among them orbit worlds more strange and beautiful than we can imagine, worlds that are waiting for us to discover their secrets. Titan is one of those worlds, and its story is only beginning to be told. Until next time, sleep well under the vast canopy of stars, and dream of orange skies and methane rains, of hidden oceans and organic chemistry, of questions that span the ages and answers that may change everything. The cosmos has given us Titan, and in exploring it, we explore ourselves. Good night.